have Alice here today for Stage 3 Virtual. I will let her take it away.
Super. Thank you so much for inviting me to give this talk. So today I want to report on some joint work in progress together with Stefan Behrens and Thomas Krau. The title for my talk is Seiberg Witten Floer Theory and Twisted Spectra. And just as a disclaimer, like this is the first time that I've ever had a talk in front of a gauge theory people audience, so we'll see how it goes. I'm from more homotopy theory background, so probably I'm gonna approach the subject from that point of view. That being said, let's just start. So this is the outline for my talk today. So first I want to discuss some Floer homotopy theory. So broadly understood, you can think of this work that we're doing is somehow under the umbrella of Floer homotopy theory. So I want to introduce that to you. So in particular, I want to give a brief introduction to Floer theory. Then I want to give a brief introduction to homotopical algebra, or the sort of homotopy theory that I come from, and sort of how I view homotopy theory as fitting in this situation. And then I want to combine those two. So I want to discuss very briefly what Floer homotopy theory is and what the program is trying to, achieve, basically. After that, I want to discuss the main sort of homotopical mathematical objects in this talk. So namely, I'm going to discuss twisted stable homotopy theory. So I want to first give a introduction to spectra. Unfortunately, there's a lot of things called spectra in mathematics. These are like the spectra of algebraic topology. So I guess most people here may not know what those are. So I want to give an introduction to that. And then I want to discuss more specifically twisted spectra, or this twisted stable homotopy theory. After that, I want to sort of apply it to Seiberg Witten Floer theory. So I want to give some brief history of this sort of program. I want to discuss Seiberg Witten equations briefly. And then I want to give a sort of sketch of where the sort of twist in the picture, where it's coming from, basically. Good. Feel free to, I don't know, ask questions and things like that during the talk. Right, so let's start with Floer homotopy theory. So Floer theory, I think most people here probably know Floer theory better than I do, but the slogan that I have in mind is the following, which is that Floer theory is some version of an infinite dimensional version of Morse theory, when only a relative Morse index can be defined. So it's going to be my working, I don't know, slogan or something. So this is sort of how I view Floer theory as working. So you have some geometric object of interest, right? And to this geometric object of interest, you assign some sort of infinite dimensional manifold, and together with some Morse Floer function on it. And then more or less, of course, there are some a lot of technical things involved here, but somehow you associate some sort of chain complex to this data, and you compute the homology groups of that chain complex, and you get I don't know, Floer homology. So for example, your geometric object of interest could be something like a symplectic manifold with a symplectomorphism. In that case, the infinite dimensional manifold would be some sort of version of the free loop space of your manifold, which is infinite dimensional. The Morse function would be the action functional. Then you associate to that some sort of chain complex, and you get symplectic Floer homology, right? So here I put Cohen-Jones-Siegel question mark. I'm gonna get back to that little thing in a moment. But let me first discuss some homotopical algebra. So I think like this is a particular subfield of homotopy theory, which I like to call it homotopical algebra. I think it's very close to what other people would call higher algebra or something like that. But I think like the definition or the sort of philosophy that vibes the most with me is the following quote by Quillen. So Quillen was arguably like the first one who used the term homotopical algebra, and he described it in the following way. He said that homotopical algebra is the generalization of homological algebra to arbitrary categories, which results by considering a simplicial object as being a generalization of a chain complex. So let me sort of try to unpack what this means, right? So I have this picture here. So we have our spaces, right? And in math, or I mean, I guess in the sort of math that we do, we like ultimately care about spaces, right? And here I'm being purposely vague with what I mean by spaces to like include a bunch of different types of spaces. This could be like a topological space, it could be like a smooth manifold, it could be like, I don't know, some space with some extra structure, just, you know, a space in some geometric sense. So what do we usually do when we have a space and we want to understand it? Well, typically we want to define some invariance on it, right? What we could do, and what we do in many cases, is that we associate some sort of chain complex to the space, and then we compute the homology groups of that chain complex, and we get some sort of nice way of telling spaces apart and telling, yeah, what sort of properties they have. So this could be, for example, like if I have a space, I could maybe, like if I have a space together with a Morse function, I could take like the Morse chains on that, give me a chain complex. It could be like I have a smooth manifold. I associate to that smooth manifold the DRAM co-chain complex. It could be, I don't know, maybe you have like some CW structure on it. You associate the CW chains to that, right? So Quillen is saying that, like, okay, so he wants homotopic algebra is supposed to be a generalization of homological algebra to arbitrary categories. So what does he mean by that, right? So what he means is that in general, like the chain complex, although it captures a lot of the things about our spaces, it doesn't capture the entire homotopic type. So if I have a space, it might be in some situations be like better to, rather than associate some sort of chain complex to that data, we associate some sort of simplicial object. And here, when he says that a simplicial object is a generalization of a chain complex, he's really like implicitly referring to this thing called the Dold-Kahn correspondence, which I've made slightly vague here. What the Dold-Kahn correspondence really says is that there's an equivalence of categories between non-negatively graded chain complexes and simplicial abelian groups. But here I'm just going to say that, you know, there's some vague relationship between chain complexes and simplicial objects. And in some sense, the simplicial object will capture more of the information about our space than the chain complex does. Okay. So what is now Floer homotopy theory? So I think, I don't know, officially, I guess you can trace back the ideas of Floer homotopy theory back to the 90s and Cohen-Jones-Siegel. And they sort of asked the question of like, okay, so if I have Floer data, what if I, rather than associating a chain complex to that data, what if I associated something that retains more of the information? So what if I constricted some sort of simplicial type object, encoding the data in such a way that taking homology recovers Floer homology? So this is where we get back to this picture again, So the Floer data is like in this middle thing, and while you usually associate some sort of chain complex here, they're asking the question, okay, can you associate something that has more of the information? So can we associate some sort of stable homotopy type to that data? I guess although these ideas have been around for a long time, it's only really recently that you've had sort of the machinery to do these things. So now my talk is like twisted spectra. So where's this twist coming from? So why are we caring about not just stable homotopy theory? Why do we care about twisted stable homotopy theory? And what does that mean? Well, Cohen and Jones-Siegel, other than just, I don't know, sketching their program of like what they wanted to do, they actually sketched very vaguely how to construct one of these Floer stable homotopy types from Floer data. So basically what they constructed is some sort of spectrum. I will come into what spectra are later on, but there's like a big problem with this, and that is that their construction of a spectrum only, or they really construct a pro-spectrum, but this only really works when our infinite dimensional manifold is trivially polarized. So what does that mean? Well, here I'm gonna do a slogan as well. So what is a polarization? Well, polarization is what you get if you consider sort of the Hessian, so you have your infinite dimensional manifold, right? And you have some Morse Floer function on it. If I look at the Hessian of this Morse Floer function, then that has infinitely many positive and infinitely many negative eigenvalues. And a polarization of the manifold is basically a decomposition of its tangent bundle, which is a Hilbert bundle, into sort of one part that contains that corresponds to like the positive eigenspace and one that corresponds to the negative eigenspace. And then you have some finite dimensional ambiguity to where you would place the zero eigenspace. And from the point of view of homotopy theory, a polarization of a real Hilbert bundle over some space X is basically a map from X into U mod O. So that's what I'm gonna take as a definition somehow. So Fruta in the early 2000s, he realized that, you know, in many of these situations where you have, like, if you're presented with Floer data, what happens in a lot of cases, like in many favorable cases, it might happen that the manifold is trivially polarized. So trivially polarized would correspond to this map being null homotopic, right? But in many situations, and then you're good. But in many situations, like you might have a bunch of Floer data where your manifold is not trivially polarized. And what do you do then? Well, Fruta, he basically proposed that you need some sort of twisted form of homotopy theory in order to account for these non-trivial polarizations. And then Christopher Douglas, in his PhD thesis in 2005, he introduced this framework for twisted stable homotopy theory, which is sort of what I want to discuss now. So that was my little introduction. So maybe this is like a good place to take questions if people have them. Otherwise, I'll just keep going. Okay, so what is twisted stable homotopy theory then? So first, let me give you a little cheat sheet of how homotopical algebra works. Here's a little table. So I don't know, like a common description of what homotopical algebra is that it's it's algebra built on spaces rather than sets. Let me briefly discuss what that means. So in classical algebra, everything is sort of built on sets, and in homotopical algebra, you build your algebra on spaces. And here's a little disclaimer. I think when people in homotopy theory speak of spaces, they don't mean spaces in the same way as geometers speak of spaces. So when we say space, we really only care about the, I don't know, homotopy type of the space. So the real line would be the same thing as a point, which I think maybe it's slightly maybe it's slightly confusing to use the word space for this, but it is the most common terminology. So I'm just, fair warning. I think better words would be something so when I don't know, when homotopy theorists talk of spaces, they really mean something that's more simplicial in nature. So maybe the Kahn complex of a space. So the singular complex of a space would be an example of a Kahn complex. There's other words for this, infinity groupoid and a homotopy type, anima. But yeah. So if you have a space, right, you typically want some extra structure on that. So the easiest thing that you can do is put some group structure on it. So you have these abelian groups, and on the side of homotopical algebra, these abelian groups are supposed to correspond to these objects called spectra that I will introduce fairly soon. You can also talk about ring structures. So an associative unital ring would correspond to something called an E1, or A infinity is maybe more common in these circles. Ring spectrum, a commutative ring would correspond to something called E infinity ring spectrum. So this also implies, I don't know, from the notation, it's also clear that there's different levels of commutativity in between E1 and E infinity. So in homotopy theory, you can't really speak of things being associative or being commutative. Strictly, you can only really say that it's associative or commutative up to, I don't know, some level of coherent homotopies. So, right, so there's a bunch of levels in here. Right, so I will come back to this. Right, so what is a spectrum, right? So here's a definition. So a spectrum is basically an infinite sequence of pointed spaces, like this, equipped with some continuous maps from the suspension of the nth space in the sequence to the n plus first space. And I don't know, I think that, don't try to stare yourself blind at this definition. I think I don't know, it's not a good definition if you'd really trying to, or I guess it is, but sometimes I feel I don't know, people try to spend too much time actually figuring out what is going on. But the important thing is conceptually they work as sort of abelian groups. Like I say here, spectra are the abelian groups of homotopical algebra in some sense. In particular, an abelian group will give a corresponding spectrum, the so-called Eilenberg-MacLane spectrum. So in this way, spectra are algebraic. And there's also a topological direction, of course. If you have a space X, then you have this corresponding spectrum to that called the suspension spectrum. So basically, you just place as the 0 space just X, and then the first space in the sequence will be the suspension of X. The next one will be the double suspension of X, and so on and so forth. But there's a number of other types of spectra which are not on any of those types. So in particular, and I think this is an important point, is that every cohomology theory, so every cohomology theory that satisfies the Steenrod, the Eilenberg-Steenrod axioms will give rise to one of these objects via the Brown's representability theorem. So in this way, you get access to, like, I don't know, different types of like K-theory spectra. So complex K-theory, real K-theory will give you these spectra. Different Bordism theories will give you spectra. I don't know, elliptic homology gives you a spectrum. There's many examples like this. And in particular, if I just look at homology with coefficients in some abelian group A, I just recover this Eilenberg-Meitingen spectrum up here. Right, so another way, or another common phrase that people use when they talk about, like, or when they try to describe what homotopical algebra is they tend to say things like, oh, it's like doing algebra but over a deeper base. So what they mean here is that there's a special spectrum, namely the sphere spectrum, which somehow takes the role of the integers. So in ordinary algebra, like, the integers is the initial commutative ring. So whenever I have a commutative ring, I can always, like, write down a map, right? There's a universal map from Z to my ring. And in this situation with homotopical algebra, there is another ring, namely the sphere spectrum, which is just, it's called a sphere spectrum because the spectrum is just like the zero space is just S0, and then the next one is just like the circle, the next one is the two sphere, the next one is the three sphere, and so on. So in particular, there's always a map from the sphere spectrum to the integers, or really like the Eilenberg-MacLean spectrum of the integers, namely the Hurewicz map. Point here also, so there's a symmetric monoidal structure on the category of spectra, with the tensor product basically being called a smash product, and the sphere spectrum is the unit of this. So this you should take with a grain of salt, like this, with this definition of a spectrum, this point isn't really true. I mean, there was a huge, like, bunch of work in the 90s done to actually get some symmetric monoidal category of spectra. So really, what you need to do is, like, you need to modify this slightly. There's many different modifications that you can do to make this be true. So you can work with, like, symmetric spectra, orthogonal spectra, I don't know, S modules, and things like that. I'm gonna sweep that a little bit under the rug and just say that, well, okay, we have this God-given category of spectra given to us, and it has a symmetric monoidal structure. And also, there's a suspension spectrum, like, there's a suspension functor on the category of spectra, and this is basically an autoequivalence. So this is, like, very similar to the category of chain complexes, right? So suspension, or like shifting your chain complex, it's an autoequivalence on the category of chain complexes, right? So in this sense, I don't know, I think, like, one way that I tend to think about spectra is, like, there's some, I don't know, beefed up version of the category of chain complexes, basically. Right, so what are twisted spectra? So as I mentioned, these were introduced by Christopher Douglas in 2005. And the slogan, I'm not going to give you, like, a precise definition, is that a twisted spectrum, and a twisted spectrum always exists over some space. So a twisted spectrum over a space X is, morally, it's a section of a bundle, but it's a bundle of categories over X whose fiber is the category of spectrum. And such a bundle is called a haunt. There's different ways of actually, like, rigorously making sense of this. You could work with, you can look at a more, like, algebra geometric definition where you're working with like sheaves of categories over the space X. There's some more, I don't know, homotopy theory. I mean, I guess that is also homotopy theoretical, but you can also consider basically just a local system of categories. You can work with, I should also mention that these twisted spectra are basically also just modules over these sort of special spectra called Thom spectra. But yes, there's different ways of making sense of this. But morally, a twisted spectrum is just a section of a bundle whose fiber is the category of spectra. And let us maybe look at one example of one of these bundles. And of course, you can construct these haunts, these line bundles of categories in much the same way as you would construct like ordinary line bundles over a space by gluing together trivial vector bundles over via like transition functions. So that is, you know, I have my space, I pick an open cover of my space. On each patch of my open cover, I look at just the trivial haunt. So that would be something like UI cross with sp, where sp is the category of spectra. This, of course, maps down to just U1 again, like the ordinary projection. So I do this over each patch, and then I give like these gluing functions. So these are basically equivalences of categories on the non-trivial intersections. So let me do that for a simple example. Namely for S1, that's pretty simple space. So here is the circle. Now this is okay. It's very light, but here I've covered this by basically the northern hemisphere and the southern hemisphere. And so yes, I cover that with two open sets overlapping a little bit. The intersection is this purple thing here. And you can just see the intersection has two connected components, right? V and W, both of these things are contractible. So basically what we need to do in order to construct a haunt on this space is we need to basically just give transition functions on these intersections, right? So on V, maybe I placed V and W wrongly here. Okay, but on one of them we glue by, okay. So we need to specify an equivalence, like a self-equivalence of the category of spectra. And I don't know, there's an obvious choice there. We can just take the identity, right? So I'm gonna glue that by just picking the identity. And then on W, the other one, I'm gonna glue by just specifying, by taking the self-equivalence given by just spending my spectrum n times. So in particular, this means that for each integer n, we have one of these haunts over S1 determined by how many times we suspend our spectrum when we go once around. Right, and it turns out that this is basically like all the haunts that exist on S1. And this has to do with classifications of haunts. So remember, like for ordinary line bundles, like line bundles are, I don't know, line bundles, complex line bundles over a space X are classified by homotopy classes of maps from X into BU1, right? So we have a similar classification here. This is essentially a theorem by Douglas. It says that equivalence classes of haunts over a space X are basically classified by homotopy classes of maps from X into the classifying space of this space called the Picard space of the sphere spectrum. So the Picard space of the sphere spectrum is essentially the space of invertible spectra and the equivalences between these. So in particular, once you have something like this, you can actually prove that the suspension spectra that I wrote down on the previous slide are the only, like up to equivalence, these are the only things that you have over the circle. So, yes.
Ian asked if there was an analog of Stiefel-Whitney classes and characteristic classes in this setting.
I don't know. I think that's not something that I've thought about, but yeah, it's a good question for sure. Yeah. But okay, so in particular, equivalences classes of haunts over the circle should just be classified by homotopy classes of maps from S1 into B-pick sphere. So that's just the same as the first, like the fundamental group of this classifying space. And then one can compute, of course, like this is not like a trivial thing, but people have computed what the homotopy group is. And this homotopy group turns out to be said. So there is one haunt for each integer n, and this is like precisely the n suspension haunt that we described earlier. Okay, so, oops. Now, I wanna discuss sort of how to go from, so the point here is that, so how do we like tie this together with what I talked about before? So there's a way of going from a polarization of a manifold to one of these haunts. So how does that work? So, okay, so first of all, like in homotopy theory, there's this really, really important map called the J homomorphism. So the J homomorphism is a map from Z cross BO to this Picard space. And morally, what this does is that, well, it takes some, so Z cross BO, it takes some real vector space here, and it sends that to some invertible spectrum. So what is this invertible spectrum? You take your real vector space, you 1-point compactify it. So now you get some, yeah, so you 1-point compactify it. So now you basically get like a sphere of some sort, and then you take the suspension spectrum of that sphere. That's an invertible spectrum. So recall that a polarization, or like from a homotopy point of view, a polarization of a Hilbert bundle over X is essentially just a map X to U mod O. So what we can do is we can compose this with a delooping of the J homomorphism to get a map like this. So U mod O, by Bott periodicity, this is just like B Z cross BO, which then the J homomorphism maps that to B pick S. And in this way, a polarization determines a haunt. And what I want to show, or the point here is that, like, yes, so if you have a polarization, then that determines a haunt. And the correct, like if you have some Floer data that determines one non-trivial polarization, then the corresponding like stable homotopy type that you would construct from this data would be just a section of that haunt. So you need to take this sort of twist into consideration coming from the polarization. Yes. So yes, I think that's what I wanted to say about that section. So any questions? Okay, so what about the Seiberg Witten Floer spectra? So I won't go into actually constructing Seiberg Witten Floer spectra, but I'm going to indicate sort of where the twist is coming from. So how do you, like, where's this twist coming from in the Seiberg Witten Floer setting? So first, I want to give like a brief history of the construction of Seiberg Witten Floer spectra. So why do we care about this, and like what has been done in the past? So of course, Seiberg Witten theory originates from physics. So originally, the Seiberg Witten invariant is something that was introduced by Seiberg and Witten, and it then proved to be very useful in the study of smooth form manifolds. And in particular, one of the things that people like about it is that you can use the Seiberg Witten theory to prove very similar things that you would have previously have proven using Donaldson theory, but you can do it in a more simple way. So one of the precursors of constructing the Seiberg Witten Floer spectra is from the early 2000s, Peruta. So basically what Peruta, I guess Bauer and Peruta, what they did is they constructed some stable homotopy refinement of the Seiberg Witten invariant using finite dimensional approximation. So rather than like having the Seiberg Witten invariant being a number, in their situation, they're constructing some sort of class in the stable homotopy groups of spheres, some equivariant version of that. And he did this using finite dimensional approximation. And finite dimensional approximation is also like an important ingredient in actually constructing these Seiberg Witten Floer spectra later on. So this really was a precursor. And in particular, he used this to prove the so-called 10/8 theorem. So there's this conjecture called the 11/8 conjecture, which is basically a conjecture about what quadratic forms are realizable as the intersection form of a smooth form manifold. And Peruta was not able to prove this entire conjecture, but he was able to do like significant progress using this stable homotopy refinement of the Seiberg Witten invariant. And also, I should say that fairly recently, there was some attempts of trying to maybe push Peruta's method further to prove the 11/8 conjecture using like some pretty hardcore spectral sequence methods. But it turns out that they were actually, so Hopkins, Lin, Scher, and Shu, they were able to show like a no-go theorem. Like you cannot push this further. You need some new input. Right, and then like the actual first construction of a Seiberg Witten Floer spectrum was done by Manolesco in the early 2000s. So he constructed the Seiberg Witten Floer spectra for basic manifolds that looked like that homology looked like spheres. So we constructed these Seiberg Witten Floer spectra for homology spheres, and then later on he used these to settle the triangulation conjecture, which was also like a big deal. Lately, Kandawit, Lin, Sasahira, they constructed Seiberg Witten Floer spectra for a larger class of manifolds than homology spheres. So they construct these as like in-pro spectra. And then in our work, we're trying to construct these Seiberg Witten Floer spectra not as just spectra, but as like these twisted spectra, taking this sort of twist into account. So let's go through some preliminaries on Seiberg Witten Floer theory. So in here, the object of interest, the objects that you're trying to understand, is some sort of pair, y comma s, where y is an oriented Riemannian three-manifold, and s is a spin C structure on y. And in particular, so once you have this, the data naturally gives you, first of all, an associated spinor bundle over y. This is a rank 2 Hermitian bundle over y. And the spinor bundle comes equipped with this this so-called Clifford multiplication, which you can view as a map from the tangent bundle of your manifold to endomorphisms of the spinor bundle. And it turns out that the space, so first of all, if you have a three-manifold, there always exists at least one spin C structure on it. So it turns out that actually the space of spin C structures on Y forms a torsor over the mapping space, so the space of maps from Y into CP infinity. And in particular, when Y is connected, the space has the following homotopy type. And roughly, you should think of the three components in the following way. So this second homology corresponds to the isomorphism classes of spin C structures on Y. And this is pretty well known. Like if you have a three-manifold and a spin C structure, then you can always get another spin C structure by tensoring your spinor bundle with some complex line bundle. Since complex line bundles are classified by its first Chern class, which is an object, which is a class in H2 Y Z. So that's sort of like where that term is coming from. These correspond to isomorphism classes of spin structures, spin C structures on Y. Then you have this thing. This, you should think of this as, so as corresponding a parametrization over a torus. This is called a Picard torus. And this KZ2, which is just CP infinity, it records an action by, it basically records an action by the circle group on your thing. Okay, so the twist is going to come from these Dirac operators. So if you're given a spin C connection, A, let's say, on the spinor bundle, one can define these Dirac operators, which depends on A. So this is a map from sections of the spinor bundle to itself. So you take your connection A, the covariant derivative, sends that, so you have a map from sections of the spinor bundles to sections of the cotangent bundle of Y, tensor the spinor bundle. And now you use the fact that you have a Riemannian structure on your manifold, so there's an isomorphism between the cotangent bundle and the tangent bundle. So now you end up in here, and then you want to use this Clifford multiplication to end up here again. Some facts about the Dirac operators. So first of all, the space of spin C connections on S forms a torsor over imaginary valued one forms on Y. So this means that, so what I mean by this is like if I take the difference of two spin C connections, then that is an imaginary valued one form on Y. So if I fix some base C spin C connection A0, if the difference between like A and A0 is this one form A, small a, we will also write dA, like d small a as being large A. Another important fact about these Dirac operators is that they're self-adjoint elliptic operators. So in particular, if we're working with like so if our space Y is compact, these are actually like self-adjoint Fredholm operators. So they have a well-behaved analysis on them. And what we're going to do is we're going to think of the Dirac operators as some sort of family of self-adjoint elliptic operators over the Picard torus. So for each point in here, yes, so each point here, so if I think of this as being the Rom homology, then yeah, I take some representative of a class here, which is something that lies here, and I guess I multiply that, like I make it into an imaginary valued one form. So I have like, and that should correspond to some sort of Dirac operator. So now I have a family of these self-adjoint elliptic operators over this Picard torus. So the twist in the picture is coming from this index class. So Atiyah-Singer index theory tells you that the non-trivial component of the space of self-adjoint Fredholm operators is actually a classifying space for K1. So that is, well, this. So the classifying space of K1 is just the infinite unitary group, like this. So in particular, I have my family of Dirac operators. So that gives me a map from the Picard torus into, so each point on the Picard torus gives me this dA, d sub lowercase a, which is a self-adjoint Fredholm operator. And since the space of self-adjoint Fredholm operators is equivalent to U, that gives me just a map from the Picard torus into U. And now I want to use both periodicity and this map, this complex J, this J homomorphism. So from this, I use basically both periodicity to end up in Z cross BU, and this maps further on to B pick S, which classifies some sort of haunt. I'm going to call that the Seiberg Witten haunt, and the actual stable homotopy type that you would have to construct from, like that you construct from the Floer data, would have to be like a section of this haunt, basically. So yes, I think that's probably a good place to stop. So thank you for listening.
Well, are there questions for Alice?
Could I just ask a question? So
yes.
Thanks very much for the talk. It's very, very interesting, rather unfamiliar angle for me.
Yes.
But one of the big stories in the using Seiberg Witten theory are perturbations. I'm wondering if how that might fit into this worldview, or this spectral worldview.
Right. I think so. The way that I understand it is that these sort of perturbations, like in homotopy theory, you're allowed to deform your things pretty drastically, right? And yeah, but yeah, you have to be a bit careful for sure when you actually, like, when defining these things, like what version of like the Chern-Simons-Dirac functional you're choosing, for example. Like if you're doing like some perturbed or some balanced one. I think so. So what we're doing is we're using some balanced version of the Chern-Simons-Dirac functional. But yeah, it's a bit unclear to me, like exactly how to formulate sort of where the perturbation is showing up in the homotopy theory world.
Thanks. Just a naive question.
Yeah.